Hey guys, this is Professor Floyd, and we're going to talk about Henry's Law. So I did a whole explanation working this out. It was long-winded, and it turned out that my webcam wasn't working right. And so I had to reboot my computer, so we'll hope that this is going to work correctly because I'm getting kind of frustrated at delivering this to the webcam. So Henry's Law is very useful. Simply stated, it's the concentration of a gas phased substance in some solvent divided by the pressure of that solute on top of the solvent. And so I think lots of times you'll see it expressed as you have some sort of liquid. Oftentimes this will be water, but it could be any kind of solvent. And then you have gas above the top, and every so often one of these gas molecules, as it strikes the surface, because gas is continuously bouncing off of these walls just as much as it bounces off of the surface of the liquid, in proportion I mean, then you end up with some of this gas that will dissolve into the water, or into the solvent of whatever type it is, in this case water. And so what will happen is we might start with a lot of concentration up top in the headspace and none in the water, but in time they will reach an equilibrium where the rate of dissolved leaving and airborne going in is equal to each other. So they reach an equilibrium. And eventually the concentration in the aqueous phase will reach some ratio to the headspace, which is the Henry's law constant of Henry, multiplied by the concentration in above. And so we express that concentration as a pressure. And so typically you'll see Henry's law constant values in chemistry textbooks as moles per liter per millimeter mercury, or per torr. And that's the conventional way of seeing it expressed. But there's also, if you look these up on the NIST webbook, you'll find that they express these as moles per kilogram per bar. So NIST really likes to use bar for some reason, and I am going to pull up my lecture slides on this that I have worked this example out already. So this is classically defined, but this is really how we will see it and how we're going to try to use it today. So this is our example. We have a 30-gallon drum, and it is full with 15 gallons of water, and it has been carelessly added 40 milliliters of toluene. So it's supposed to be a water disposal drum, dirty water, processed water, and somebody accidentally added some organic solvent to it. So we're going to ask ourselves, what's the headspace concentration of toluene? What's the aqueous concentration of toluene? So to do this, we can start from a few different places. One place that's a good starting point is how many phases are present. At first, well, of course, we have liquid toluene. So we have some liquid toluene, and then it's going to evaporate, and then some of it will come down into the water too, right? But how much will go into the water, how much will stay in the air, and will it all evaporate? That's the first question we need to ask ourselves. So to check to see if it will all evaporate first, we need our Henry's law constant, which I've already looked up on the NIST. So you can see my units are moles per liter bar. And we have our vapor pressure, which I calculated using the Antoine equation. And I've discussed how to use Antoine equation on homework set 2, I think problem K. So you can look that up on your own. Those of you in class with me, you can just go back, pull up that spreadsheet, and then go to the NIST website and type in the values for toluene for the A, B, and C for Antoine equation, instead of, I think it was ethyl acetate was the example that we worked there. So type those in and you should get 28.45 torr. Okay. So at 28.45 torr, that's definitely a pressure. We can calculate what the concentration of toluene will be in the water. We can also use this pressure to calculate what the concentration is in the air. These are both at saturation conditions. And then we'll multiply those concentrations by the volume. Each one of these is 15 gallons. So 15 gallons times 3.78 liters per gallon is equal to 56.7 liters. So let's just remember that our volume, actually of both of these, is 56.7 liters. Okay, so first let's start with our vapor pressure. So this is the pressure of vapor at 25 C and 1 atmosphere. So we have 28.45 torr in the environment, which is coming from our toluene, but the overall environmental or atmospheric pressure is 760 torr. So that gives us a ratio, and that's a really small ratio, but if we multiply it, it's not that small, but if we multiply it by 1,000,000, then that gives us parts per million. And so 28.45 divided by 760 times 1,000,000 is equal to 37,434 ppm. Alright, so we're just going to round that to 3 significant figures. So 37,400 parts per million. So those parts per million, those of you that are in industrial hygiene, environmental world, you know that we can convert parts per million pretty quickly to milligrams per cubic meter by multiplying by the molecular weight and dividing by molar volume. If we do that, then the units work out, and it gives us from parts per million to milligrams per cubic meter. So this multiplied by molecular weight, 92.14 grams per mole, and divided by molar volume, 24.45 at this temperature and pressure, which is 25 C and 1 atmosphere, is liters per mole. So the moles cancel. The grams per liter end up working out when you do the conversions. They cancel out the parts per million. You have a million-fold difference. So anyways, this comes out to milligrams per cubic meter. And then I guess I can calculate that real quick. Times 92.14 divided by 24.45. Alright, so that's 1.41 times 10 to the 5th milligrams per cubic meter. But we don't really want milligrams per cubic meter. Liters would be more useful since that's what our volume is in. And we usually talk about air in cubic meters, but water in liters. And so it's going to be helpful, just trust me, if we put all this in liters as our base unit instead of mix and match. So if we convert 1 cubic meter is equal to 1,000 liters, we're just going to divide this thing out by 1,000, which is going to take 3 away from our exponent, which gives us 1.41 times 10 to the 2, or times 100, so 141. All right. So that equals 141 milligrams per liter. All right, so at saturation, this is our concentration in the air, toluene in Headspace. That says Headspace. And we can then use this pressure here, or this pressure, and Henry's law to calculate what the concentration will be in our solution. So the concentration aqueous is going to be equal to Henry's law constant, which is 0.15 moles per liter bar. Sorry, I didn't know that this is given in moles per kilogram bar by NIST, but because it's water, we can simply multiply by the density, which is 1 kilogram per liter, and convert this into moles per liter bar. So you could do that for any solvent. You just have to multiply by the appropriate density. Water is 1. You know, hexane or toluene is 0.87. So if we were dissolving into toluene, then we would multiply that constant by 0.87. It would get smaller, but then it would be expressed in liters per liters instead of per kilograms. So 0.15 moles per liter bar multiplied by our pressure, 28.45 torr. Of course, torr don't cancel bar, so we have to convert our torr into bar, and 1 bar is equal to 750 torr, 750.066. So 750 is close enough. Our torrs cancel, our bars cancel. We're left with moles per liter. But we don't really want moles per liter. In the environmental world, we talk about parts per million, but really that's milligrams in liquids. That's milligrams per liter. So milligrams would be 1,000 smaller than base unit. Liters would be 1,000 larger than a gram. And so it'd be a kilogram of mass of water. So that's where the parts per million come from. So in this case, we want parts per million, so we've got to get out of moles and into a mass unit. And so we're going to do that with our molecular weight. So our molecular weight is 92.14 grams per mole. All right, so now our moles are gone. We're in grams. Now we want milligrams, so 1,000 milligrams per 1 gram. All right, so now we've got milligrams per liter. And that comes out to 0.15, 28.45 divided by 750 times 92.14 times 1,000. Okay, so 524.3 milligrams per liter. Okay, 524.3. Yep. All right, so now if we say, like I said earlier, we're going to then take these concentrations and multiply them by the volumes to see if we have a saturated condition. So if the masses in the air and the mass in the aqueous phase are greater than the mass that was input, the 34.8 grams, then we know that we have excess capacity, and so we're not saturated. So we'll have to calculate precisely what our ratios are. So our mass in air is equal to our concentration in the air, which is 141 milligrams per liter, multiplied by the liters, which is 56.7. So that's going to be milligrams, 141 times 56.7. So that's 7,999 milligram, or 995, which is basically 8 grams. And then the mass in the aqueous phase is going to be 524 milligrams per liter, multiplied by, again, 56.7 liters. So that's going to give us milligrams, so 56.7 by 524. So that comes out to 29,708. So milligrams, which is also 29.7 grams. All right, so we can add these two up, and we can see that we're going to be excess capacity. So 29.7 plus 8 is 37.7 grams, but we only put 34.8 in the system. So we have a problem. Not really a problem, we just know we're not at saturation. Since the concentration or the vapor pressure is going to drive the concentration in the liquid, then we know that the headspace won't be saturated, because if we saturated the liquid, then we wouldn't have enough mass available to saturate the headspace. Well, if the headspace isn't saturated, then the liquid is going to off-gas into the headspace and fill it to some point. Well, once it starts off-gassing into the headspace, it will no longer be saturated either. So we're going to come to some happy medium place that's close to saturation, but not there. And so how do we calculate that? We could go and set up systems of equations, like what's shown on the desire to learn, but we can also recognize that we've simply expressed our Henry's law constant in terms of concentration in the headspace versus concentration in the liquid. And we've done that at a particular pressure of 28.45. But this ratio is the whole principle of the constant. There's going to be a constant ratio between headspace concentration and liquid concentration. And those values are going to be what we've calculated here, the 524 milligrams and the 141. So it's these guys. Alright, so this is basically an expression of Henry's law. And we see that in the air, we have this concentration. In the water, we have this concentration. So if we let this equal x, then what will this equal? Basically, if we let this equal 1, then what is this? So we can calculate that pretty simply by saying 524 divided by 141. So 524 divided by 141, and that equals 3.716. So this is 3.716 times larger than 141. So now we've got them in the same terms that deal with some unknown. So now we can start thinking from a mass balance approach. We input a certain mass, 34.8 grams, 40 mils of toluene. That toluene disperses in time between the air, the headspace, and the liquid phase. And it will do so with 3.716 times as much concentration in the liquid as in the headspace. So now, since we've got a known mass, we've got to set this up on a mass balance. So how do we do that? It's really not very complicated. Let's get rid of this though. Give myself a little bit of space here. So we have a mass of toluene, and that's going to be equal to our concentration in the aqueous phase times the volume aqueous phase plus our concentration air times the volume air, right? So we have this concentration in the aqueous phase, that's 524 milligrams per liter, and then we have, it's 524 milligrams per liter, which is equal to 3.716x. So that's what we're going to plug in here, is 3.716x, and then multiply that by our volume, which is 56.7 liters. Then we're going to add that to our concentration of air, which we said let our C air equal X, C aqueous. So X times 56.7 liters. And so because these base units are milligrams per liter, we know that these liters are going to cancel, and we'll be left with milligrams, and this will be left with milligrams. And we know that we have 34.8 grams, or 34,800 milligrams have been input into the system. So we combine this, we do our algebra here, 56.7 plus 3 times 56.7, so times 56.7. This equals 210.7, that's just 56.7. So all in all, we have 267.4 x liters, because x is milligrams per liter, and that's canceling out the milligrams that's implied. And that is equal to 34,800 milligrams, which is true. So we simply divide out by 267.4 liters, 267.4 liters, and we're left with milligrams on this side. Right? We're left with milligrams per liter, which is our original units, milligrams per liter. Okay. And so x equals x equals 130 milligrams per liter. So remember that C air equals x equals 130, and C aqueous equals 3.716 x. And so 130 times 3.716 equals 484 milligrams per liter. And so that is the answer to our question. What is the headspace concentration of toluene? It is 130 milligrams per liter. What is the headspace concentration? What is the aqueous concentration of toluene? It's going to be 484 milligrams per liter. We could take this another step further, and maybe I'll do this on the exam, and I could ask you what mass is distributed. What's the mass distribution in the headspace and in the aqueous phase? In which case you just simply multiply the concentration of the aqueous by the volume of the aqueous. So multiply by 56.7 liters and you have milligrams. And then do the same thing with the headspace. We have 130 milligrams per liter, 56.7 liters. That comes out to some number. And yeah, in this case, the mass ratio will hold true to this concentration ratio because we have an equal volume in both the air and the water. But if we hadn't started with an equal volume, if we had started with 20 gallons of water, then both of these numbers would have been lower. But when we looked at the mass distribution between headspace and water, it would have been very different. It would have been different than this ratio of 3.71. Maybe that was confusing. If so, disregard it. But I'm only talking about the mass distribution being different than this. The concentration will always be 3.716 because that's a function of the Henry's law. For toluene at 25 C at 1 atmosphere of pressure in water. So if you put it into methanol or ethanol or something else, then of course it would be a different value. Alright guys, I hope you find this helpful, and I'm sorry it's so long-winded. You can fast forward, do things, reverse, rewind. I'll see you in class.